So I have these two spheres. I want you to think of these as bowls. So I have a bowl that's concave up and a bowl that's concave down. So just a cereal bowl. In the middle of the cereal bowl is a place of equilibrium. And what I mean ultimately is that, and let me just draw this in here like a line. If I put a marble in the bowl, say right here, the marble is going to oscillate back and forth about the equilibrium position. Does that make sense? So just have a bowl. This is considered a stable equilibrium. Right? Stable because if I displace the ball further to the side, there will be a force that will attempt to displace the ball back towards equilibrium. Now, I'm not suggesting that this object is in simple harmonic motion. Simple harmonic motion is a specific condition. I am suggesting that this marble would be in harmonic motion, that it would roll back and forth across the bottom of the bowl, and that it would do so in a regular way that would repeat itself. Can you all kind of agree with that? It has qualities that might make it a simple harmonic oscillator. But in order to be a simple harmonic oscillator, it has to be able to be modeled by a sine or a cosine function. And it has to be experiencing a Hooke's law restoring force. So before I could state that it's a simple harmonic oscillator, I would have to prove one of those two things. I'd have to prove either that the force acting on the marble can be modeled through Hooke's law, or I'd have to prove that the motion of the marble can be modeled by a sine or a cosine function. Now, what we're going to learn to do is show how forces can predict whether an object is in simple harmonic motion or not. That's what we need to do. But I want to be very careful. Hooke's law has some very specific dependencies. And although it looks super simple, it's just a linear function, it's a vector equation. And the negative sign is critical in that equation. What it states specifically is that if I displace the object to the right, there will be a force to the left. That's the negative sign says. The size of that force is proportional to the displacement. So if I double the displacement, I will double the force. I don't know that the circle does that. I know that if I displace the object to here, whatever that angle of inclination is, that's going to determine the acceleration back. And if I double that, does it double the angle? Does it? I don't know. I'd have to show that there's that kind of proportionality. That's why I am not sure if this would behave as a harmonic oscillator or a simple harmonic oscillator. I do know that if I turn the bowl over and I put the marble on the top of the bowl, that it would also have an equilibrium, that I could probably balance the marble at the top of the bowl. Would this be a stable equilibrium? If I displace the ball a little bit to the side, will there be a force that will attempt to put it back to the middle? No, this is an unstable equilibrium. Although it is an equilibrium, this force doesn't appear to have a minus sign in front of it, does it? In fact, if I were to displace it a small amount, there will be a force that will cause the object to accelerate away from equilibrium, and probably getting faster and faster. In fact, I would say that force increases because my angle here is not as steep as the angle here. So I would think this will not be an oscillator for sure, but this might have some kind of exponential change in its velocity as that angle gets steeper and steeper. I'm not sure an exponential would describe it though. I would have to do the math. In fact, I don't think it would because eventually it would just be vertical, right? Reach the side, and that would be a constant from that point forward. I'm bringing this up because we're going to be faced with other kinds of oscillators. Your job is going to find a way to see if your oscillator has a behavior that is proportional to displacement and whether there is clearly a force that is back towards equilibrium. In our spring mass oscillator, it's clear that that's true. When I'm on the right side of this diagram, the force in the spring is to the left. When I'm on the left side of this diagram, the force in the spring is back to the right. this system is going to cause there to be a restoring force back to the middle. And since it is a spring, we know that that force will be proportional to displacement. The spring mass oscillator is the most basic oscillator. So what we have to do today is we have to do the math. You have to figure out a way to show x as a function of t, starting from here and ending with x as a function of t, v as a function of t, and a as a function of t. Now, we've done stuff like this before. We did it first semester, and that's where we learned the basics of calculus and the polynomial function. And we got more complicated ones. If you remember, we had an example where we dropped a coffee filter. And we said that it was experiencing a downward force of weight, an upward force that was proportional to velocity. And we asked, could you come up with an expression for the motion of this object? Do you remember what you had to do to find an expression for the motion of this object? I guess not. You would have said something like, I would have said something like, you need to come up with a differential equation that could be used to determine velocity as a function of time. I would have told you to start here. And since you didn't know this, I'm telling you, you need to have a starting point. And the most likely place to build a motion equation is from Newton's second law. And the reason is obvious to me, but maybe not to you. Acceleration is directly related to velocity. They're related by the derivative. And velocity is directly related to position. They're related by the derivative. Newton's second law starts with a differentiable equation. So if we write the forces in, you can immediately get an equation that could be solved for velocity as a function of time. Start with Newton's second law. Take a minute, write that into your notes somewhere, that if you're asked to find a motion equation and the object does not have a constant acceleration, you should start at Newton's second law. You'll have to create a differential equation. It's going to be tough. But this is where you start, Newton's second law. All right, our object has been displaced from equilibrium. We'll put this blue line. This is equilibrium. Our object is located some distance x away from equilibrium. It was started at some initial position. It's not there now. It's moving a little bit to the left. All right. Getting back to where we were before I got disturbed, let's assume the object had been started a distance x naught from equilibrium. I'm saying this because I want to set up some initial conditions. At time equals 0, the position of the object was x naught. We pulled it out and released it. That's time equals 0. And at that moment, the object had no velocity. These are our initial conditions. So if you're looking at the other screen, our object started at some initial position, and at that moment, the velocity was 0 when the object was released. After that, the object is experiencing an unbalanced force. That force is from Hooke's law and is causing an acceleration. So if we start with Newton's second law, that gives us a place to begin. This is a spring mass system, and the only force that matters is going to be the Hooke's law force, because weight and normal force are not contributing to the motion of the object. Now, if we say that there's friction here, that changes things, and I would have to consider weight and normal force because they would be contributing to the motion of the object. But for this example, let's assume that there is no friction. We're dealing with no air resistance. We are trying to do the basic oscillator. That would mean that the unbalanced force is that due to Hooke's law? I'm writing certain things in yellow as a sign to you guys that I think these are things you should be able to do and know why we're choosing them. When I write other equations that are not in yellow, I'm saying these are things that I want you to see how it was done, but the results are going to be more important than those transitions. You will not be expected to do those things on a test. But to set up a differential equation that could be used to solve for position as a function of time, I expect you to be able to do that. And that's what we're doing right now. A brief reminder, acceleration is already a derivative, and velocity is already a derivative. So the next step that you would have done if you're trying to create a differential equation is to substitute dv dt for x. The problem is that when you do a substitution like this, your hope is that you're going to get a function now that is now all in the same variable. And we don't. When I substitute dv dt in for a, I introduce velocity, but I still have position. So the only way I'm going to be able to get this in the same variable is if I substitute again for v. Now this is telling me something very specific. It says if I take the position function and I take the derivative twice, then I get the position. It's not ideal. And that's not really the way it's supposed to be read. But this is a differential equation that could be used to solve for x. The problem is that it's the second derivative. So everything we learned about how to split a derivative isn't going to function here. We're not going to be able to do those things. In fact, there's a certain symbology that's used here, and you need to be versed in that symbology. Instead of writing it like this, which is very cumbersome, we have a shorthand where we say, well, it looks like d squared, and it looks like dt squared. So we're going to write a second derivative like this. This is also known as a second order differential equation. The order of an equation is the number of derivatives that are within it. So a second order differential equation has a term that is the second derivative. I think that sounds obvious, but the order of a polynomial is based on the highest power of that polynomial. So the order of a differential equation is based on the highest derivative of that equation. You should also be aware that in college, it is likely you will encounter professors who don't write it this way, who use shorthand for stuff like this. One of the most common shorthands is dot notation, where a single dot represents the first derivative with respect to time, and the second dot represents the second derivative with respect to time, and so on and so forth. It's usually specifically referring to time, usually. But you will encounter folks from other states and other countries who have been writing in dot notation for a while, and they write it like it's just second nature, and you will have never seen it before. So now you can't say that. I'm not going to use the dot notation because it's inappropriate for us at this level, but once you have advanced some, dot notation is pretty ubiquitous and obviously saves you a lot of writing, especially in a complicated equation that might be fourth order or third order, where you might have more complicated things in the equation. Now, I want to rewrite this just a little bit because I want to do what we talked about when it came to differential equations, and that is isolate the differential. This is a differential equation. It is telling you how two functions are related. The function for acceleration and the function for position. It's telling you how they're related. It says that there is somewhere in the universe a function for position, x, as a function of time, that when I take the derivative twice, produces a negative sign and a constant, and the original function. That's what it says. Do you know a function that when you take its derivative will get you back the original function? Everybody in calculus does.
E to the x.
Well, in this case, e to the t, right? Because our functional variable here is t. So if I take the derivative of e to the t with respect to t, what do I get back? E to the t. In fact, what we are doing, because you don't have a method, is we are guessing at what the answer should be. We are guessing a solution. Chapter 1 of differential equations has you just guess at an answer and see if it works. So I'm guessing. Here's my guess. My function will be x naught e to the ct. I got to put a constant in there because I need in my derivative to produce a constant. And so I'm putting it someplace where I know the constant will be produced because I know the chain rule. So everybody who's in calculus understands this. And that's why I'm writing this in blue now, right? I don't assume that you all have done this in calculus yet or are in calculus. If I take the first derivative of this function, I will get x naught because it's just a constant. And when I take the derivative of e to the ct, what do I get back? E to the ct. But I have to obey the chain rule, which does what? I have to take the derivative of ct with respect to with respect to t, which is going to produce a constant. So if I rearrange that, I get c x naught e to the ct. That is my first derivative with respect to t. I'm going to take the next derivative with respect to t. I'll get c x naught e to the ct times c. Right? C and x naught are just constants. And then e to the ct, the derivative of that is just e to the ct times the derivative of ct, which is c. So that's my function. Do you all see that this function is c squared times x? Because this is my original function, and there's the function sitting right there. Do you guys see that all okay? Did I do it? Did I guess the right equation for this? I took the second derivative. I got a constant times my original function. Did I get a negative sign? No. So this won't work. And I knew it wouldn't work. I said already that it wouldn't work, said at the very beginning. Is my position going to keep going in the x direction exponentially forever? No, this was never going to work. Now, I could manipulate it. I could put a negative sign here. I know, and you guys probably could figure out if I put a negative sign here, it'll pop out a negative sign, won't it? It'll put a negative sign right here, which will mean that I'll have a negative sign there. But when I go to do this another time, what happens to that negative sign? It goes away. So that's not going to work. I need to guess a different function. Now, come on. You guys all know where we're going with this. Anybody who's in calculus knows where we're going with this. What is a better function for us to choose? Sine or cosine? Now, if you didn't know that, that's because you haven't been in calculus. But what I'm going to talk to you about right now, you must know by the time we're done. So we're going to start by describing two possible functions. And everybody in pre-calc, my understanding is you've just done all sorts of stuff about graphing sine and cosine and tangent. And you know things like phase shift. And you know what all the different variables do to change the sine and the cosine function. I'm expecting I can count on that knowledge without having to reteach it since it was just taught this year. Fair enough, all of you pre-calc folks? So x equals x naught sine ct. That's a possible function. And x equals x naught cosine ct. I'm putting the x naught out front just like I did before because remember, I'm looking for a position, and I know the position has a maximum x naught. The e in the prior problem was just going to be a scaling value with no units. The sine and the cosine, similar. They're going to be a scaling value with no units. So I need to multiply by what I think is going to be the maximum of my function. That's why x naught is there. Now, we got to test this. Our test is going to be to take the derivative. And my expectation is when I'm done, you can do this without any difficulty. You need to know how the derivative of the trig functions work. So let's start. dx dt. The derivative of sine is cosine. So it's x naught cosine ct. But I have to use the chain rule, so I have to take the derivative of ct with respect to t, which just produces a constant. Reorganize it, and I'll get c x naught cosine ct. All right, smarties, what is the derivative of cosine? Negative sine. So I'll get x naught times negative sine ct. Chain rule requires to take the derivative of ct, so that produces a c. Rearrange it. And I'll get negative c x naught sine ct. All right, you guys do the next one. You've seen both possibilities now. You should be able to produce the second derivative by just taking the derivative one more time. Try it. It's all in. Can't spend too much time here, so I'm hoping you have negative c squared x naught sine ct and negative c squared x naught cosine ct. Now, this is acceleration, this is velocity, that's position. Same over here. This is velocity, that's acceleration. The question comes down to, does this model the behavior we started with? Does this fit the pattern for our second order differential equation, this one? Do we get back a constant, a negative sign in our original function? I'd say we do. This portion of the function is just x, and this portion of the function is just x. Now, I want to be done there, but we have a long way to go. So both of these solutions are right, and they're fine. Which one matches our boundary conditions? I know the E&M kids know the answer to this, but you guys in mechanics need to know the answer to this. Which one matches our boundary conditions? Cosine, because x equals x naught when time equals 0. And only one of these functions is a maximum at time 0. Sine is 0 at time 0. But cosine is 1 at time 0. So the cosine function better models our system. Now, there are oscillators where the sine function would model it better. But for most of ours, we're going to use the cosine function to model our system. We got more to do, so I'm going to kind of tidy this up if that's okay with all of you. This creates 3 functions for us to kind of put together. Our 3 basic starting points for our motion equations. But these were predicated on this second order differential equation. But what we actually produced here is a little different. This is what we get from looking at the spring mass system. But this is the basic oscillator function. It says quite clearly, x is your function that describes position. If you take the derivative twice, you get the square of a constant and a negative sign. Now, every oscillator has to have a differential equation that fits this pattern for it to be an oscillator. That's what makes it an oscillator. And that's why Hooke's law is so good as a starting point. Every oscillator will have a second derivative that produces a negative sign, a constant, and the original function. That's the definition of a harmonic oscillator. And not just any harmonic oscillator, a simple harmonic oscillator. Because the solution to this equation is a set of functions that show that the motion of the object is based on sine and cosine. So if you can produce any differential equation that has a negative and a constant related to a position and an acceleration, that's a harmonic oscillator. And ultimately, what you really want to be able to say is A equals minus c squared times x. It's always going to be from Newton's second law, either for torques or for forces. And A can be alpha and theta, and it's still the same thing as long as it's minus c squared, some constant here. It's a second order differential equation with a single kind of response. What that means for a spring mass oscillator, well, this is the constant for a spring mass oscillator. So what does C equal for our spring mass oscillator? It's staring right in front of you. Can you see what C has to equal? What? Somebody say it. That sounds like a lot of mumble. C has to be the square root of k over m. Has to be. Right? They're in the same spot. That means any place where there's a C, you replace it with the square root of k over m. So now we're not talking about any oscillator. We're talking about the spring mass oscillator. Right, we have found our constant. So where I see a C, we'll replace it with the square root of k over m. Now these aren't generic, these are the spring mass oscillator functions. They describe where the object is, how fast it's going, and its acceleration for every moment in time, from the moment it's released to the moment it stops oscillating. Every oscillator needs to form an equation that looks like this, and wherever there's C, you replace it. There's more to say here, but are you catching on a little bit to this? By the way, C is often called the angular frequency. Look where it is in the function. It shows up here inside the equation for the cosine or the sine. And I'm multiplying it by time, which means the unit for this has to be radians per second. It has to be. There's no other way this works unless the inside of that parenthesis is in radians. Moreover, this tells us something else. When is cosine equal to 1? when the inside of this goes by 2 pi, right? So that means my system repeats when this equals 2 pi. Notice I'm putting a capital T there because this is when the object comes back to its original position, is when everything inside that parenthesis has increased by 2 pi. This has got to be how long it takes for my system to repeat. This is what's on your equation sheet. This is the period of a harmonic oscillator, a spring mass oscillator. It's taking everything inside that cosine function and setting it equal to 2 pi, and then solving for time. All right.